This video shows you how Prim's algorithm finds a minimum spanning tree in a weighted undirected graph. A spanning tree is a connected and acyclic subgraph that contains all vertices. For example, the vertices and edges in red are a spanning tree for the graph. The weight of the spanning tree is the sum of all edge weights. In this case, the weight is 33. In green, you can see a different spanning tree, where the weight has increased to 47. The goal of Prim's algorithm is to find a spanning tree with minimum weight. Let's go through Prim's algorithm step by step. Prim's algorithm iteratively adds a connecting edge with lowest weight such that no cycle is created. We keep track of the lowest edge weights of vertices to the current tree in the table below. Start with an empty tree and set all weights to infinity. Choose an arbitrary vertex. In this case, I pick vertex A. A can be reached by edges to B and C with weights 6 and 2. We add C and the edge AC because 2 is smaller than 6. At this point, there are 3 edges that connect the tree to the neighboring vertices B and E. We go to B via edge BC because the weight of 3 is the smallest. Notice here that the edge from A to B has the lowest weight of all blue edges. But we must ignore this edge, because both A and B are already in the current tree, and adding this edge would result in a cycle. That's why we pick edge CE with weight 7 instead. Now do the same steps iteratively. At this point, we want to go to vertex F, but there are 2 edges with lowest weight 8. In this case, you can pick either edge. I choose edge EF. Finally, we go from F to G. That's it, we are done. That is our minimum spanning tree, and the weight is 15. Let's wrap up with some key facts. Prim's algorithm is a so-called greedy algorithm. The graph in Prim's algorithm has to be weighted and undirected. Prim's algorithm works also if, as in the example before, some edge weights are negative. In general, the minimum spanning tree is not unique, so there can be different minimum spanning trees for a graph. But if you have a graph where all edge weights are different, then you can be sure that there is exactly one minimum spanning tree. The time complexity depends heavily on how you store the minimum edge weights. If you simply use an adjacency matrix, Prim's algorithm is quadratic in a number of vertices. But the time complexity can be reduced by using various heap data structures as shown in the table. Thanks for watching, everyone. Please let me know in the comments about what algorithm and content you want to see more videos on. Cheers, and see you in 2 weeks.